Okay, so far we've learned all about sets and how to count them, how to tell what's a subset, and all that. But the concept of a set is somewhat limiting because many times we want the order of the elements in a set to be important, but sets are unordered. So in order to deal with something where it's important to have items in a set ordered, we need a new structure. And that new structure we'll call n-tuples, ordered n-tuples. So we get a new definition. We'll say the ordered n-tuple A1, A2, dot, 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 AN is the ordered collection that has A1 as its first element, A2 as its second element, and then we'll do a dot, 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 and a n as the nth element. All right, then we say that two ordered n-tuples are equal if and only if each corresponding pair of their elements are equal. So, in other words, A1, A2, dot, 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 AN is equal to B1, B2, dot, 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 BN if and only if AI is equal to BI for I being equal to 1, 2, dot, 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 going up to n. That is simply your index number saying the first element, second element, and so on are all equal. And we can say, in particular, ordered pairs, that would be two tuples, the ordered pairs AB and CD are equal if and only if A is equal to C and B is equal to D. And we should put a special note here and say, note that in set A and B and set B and A are not equal unless A is equal to B. All right. Okay, now that we know what ordered tuples are, we can talk about a Cartesian product. Leads us to a new definition where we'll say, let A and B be sets. The Cartesian product of A and B, denoted by AXB, it's like a multiplication sign there, is the set of all ordered pairs A and B, where A is in set A and B is in set B. Notice this is all possible combinations of how you can combine these ordered pairs together. So we can write this as a Cartesian product B is equal to, set builder notation here, the set of all ordered pairs A and B such that A is in set A and B is in set B. Okay. So we can do, say, an example here. Go let A represent the set of all students at a university and let B represent the set of all courses offered at the university and then we'll say, okay, what is the Cartesian product A and B, and how can it be used? So to look at this, we need to say, all right, the Cartesian product of A and B is all ordered pairs of the form A and B, where A is a subset I'm sorry, where A is a student at the university and B is a course offered at the university. We can use the Cartesian product to get all possible combinations of students in classes. Interesting to note, a little side note, in relational databases, if you query two tables without relating them, you get a Cartesian product. So if we had this previous situation here, where we had students at the university and courses offered at the university, and we ran a query on the students table and the courses table without relating which students went with which course, we would get a Cartesian product. That would be all possible combinations of all students together with all courses. And that's a common error in database work. However, it can also be useful if you're looking to try to get all of the possible combinations. A relation is a subset, so we'll call a subset R of the Cartesian product AB is called a relation from set A to set B. The elements of R are ordered pairs where the first element belongs to set A and the second to set B. For example, R equals the set of, say, A0, A1, A3, B1, B2, C0, C1, C3 is a relation from set ABC to set 0, 1, 2, 3. All that we're doing with a relation here is defining some method that the elements in set A relate to the elements in set B. So we could do an example. Say, what are the ordered pairs in the less than or equal relation, which contains order pair AB if A is less than or equal to B on the set zero, one, two, three. So in this case, we're doing a relation from this set to this set using a certain rule, the rule being A is less than or equal to B. So we can say the ordered pair AB belong to relation R if and only if both A and B belong to set 0, 1, 2, 3, and A is less than or equal to B. So the ordered pairs would be 0, 0, because A is less than or equal to B in that case. 0, 1, 0, 2, 0, 3, 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, and 3, 3.